3. How would you know if I solved it correctly? Substitute it back in here and see if it makes a true sentence. Yeah, it's 3 plus 3 equal to 7. No, so I solved it incorrectly. And that's what we're going to do with differential equations. We're not solving them. We're going to give you solutions to the differential equations, and you are going to see if they make a true sentence. So we have to remember what a differential equation is. Remember, we had to memorize this last year. What is the differential equation? It's an equation, not just x and y's, involving what? If it's a differential equation, we need derivatives. But when I solve a differential equation, I'm not looking for numbers. What am I looking for? That's right. The solution is not a number, but the solution is a function or a relation, because it could be a relation. So when we did implicit differentiation, and remember we had x times y equals 1, and then we didn't solve for y, but we took the derivative as written. And so it was x times the derivative of y with respect to x, plus y times the derivative of x with respect to x, and that's equal to 0. If you solve for dy dx, it's equal to minus y divided by x. That's a differential equation. We say it's a diff EQ. So really what's happened is somebody has taken maybe an equation, or maybe they're just collecting data, and they took the derivative, and I want to undo it. I just want to figure out what the function was. And there's a step-by-step process, but we're not going to do that today. We're just going to look and see what the derivative tells us. Okay, Matt, you need to sit someplace else? Okay. We need a model for population growth. Okay. And we have some basic assumptions. But I'm going to look at it a little differently. I'm going to look at qualitatively. Quantitatively gives me actual numbers and answers. Okay, Kevin, you're going to miss this. And this is the whole flavor of this section. It's different. It's different from anything you've done. So I have to go through it. Now, what would be an assumption about a population? It's growing. The population's growing. Unless we're talking superflu, generally it's okay. So what's true about the derivative if the population's growing? That's positive. So when I find my differential equation, I have to make sure that my population growth would be positive. What happens if the population is 0? Do you have any growth? No. So dp dt would have to be equal to 0. When the derivative is equal to 0, it's called an equilibrium. And this, you can get a whole course on solving differential equations. Lots and lots of tricks to solving these things. Now, what if the population is decreasing? Because can that happen? When would the population be decreasing? Starvation. Oh, and guess what they're going to start doing? They're going to start letting people hunt wolves.
Yeah, that's going to be awesome.
I'm doing my best to fight it.
What do you say? Why is it bad to hunt wolves?
Why are they letting people?
Because they almost are extinct.
And there's
So-
too many of them.
You can get a lot.
Why would
You
they
can
let
have
a
the lottery to
bunch
get a
of
wolf for Minnesota.
No,
Yeah.
they're not extinct anymore.
No, but they're not a strong population
Yeah,
either.
they are, because they're around here.
I've never seen a wolf
Why do
here.
we need those?
Wolves?
Yeah.
Because everything balances everything. That's the problem. When a species becomes extinct and you unleash something else that's bad, which is why we have zebra mussels here. Okay. Okay, why would the population be decreasing? We got hunting, what else?
Oh, white one.
What else would cause the population to decrease?
Shortage of food.
Shortage of food, lack of resources.
I've never really ended anything.
Lack of land. Okay?
Usually nothing to do with math. What?
Oh, this has everything to do with math, because what math is used for is to model real-world situations.
That's not you get a piece of talking to.
What? Why? No. I know what you're talking about. Okay, wellness. Okay, instead of writing a specific person, genocide. It's still going on. That's mhm. Yeah, it's still going on.
You guys hear what that leader did?
Okay,
The leader of the 2012 or something? Yeah.
hey guys, you guys, what else happens in the world? Natural disasters. Okay, so when I'm trying to, okay you guys, Nicole, Matt, when I'm trying to find a differential equation that models, girls, that models population growth and actually decreasing in population, I'm going to try to find a differential equation that will work with this. And we're just going to like kind of guess through it what it would look like. So first off, if we do, whoops, if we say dp dt is proportional to the population, what if the population is 0? What's dp dt? It's 0. Okay? So I've got my equilibrium. If the population is positive, what's true about my change in population? It's positive. Okay? But I don't get this decreasing thing. And by the way, this is a nice this is a nice differential equation assuming a small population.
Wait, so does it fail when does it fail?
It fails when the population gets large because what's the solution to this? Because you know what it is, because somebody's already said it. It's paired. I call it e to the kt. You could use r. It doesn't matter. Mm-hmm. And what does it look like? It looks like this. Okay? You can talk about, you guys, you can talk about our economy. For a long time, it was growing exponentially. Then what happened? About 4 years ago. We had crises. Because, you know what? We can't keep growing like that. We have limited resources.
Did you just say like that?
McDonald's. It's still like
Right. And this is, yeah, exactly like this, you guys. Shh, Matt. You know, on the MCAs, hey guys, he is lately. On the MCAs, we've had a growth rate like this, and now they're assuming it's linear. Here is 100%. Can you get higher than 100%? No, there's no extra credit on the MCAs.
I can.
You can't, because there's no extra credit, and so it levels off like that. Well, unfortunately, the state has this model, and so we have to have a certain percent increase in our MCA scores. But if you think about the fact that we're already at whatever 90-some%, it can't keep increasing at that fast rate because it has to hit 100. It can't go beyond it. So even if it hits 100, it's still going to have to level off. So it's not a good model, and it's actually impossible for us to achieve that because they don't want to give us any extra money.
They could just
Also, I don't think they really realize that this model doesn't work when you're up here. It works great when you're at a small population. It's a good model, but it doesn't work here. So we're going to have to fix the problem here. I would like, because what's going to be true about my population, it can't keep growing like that because you just told me we might not have enough food. So guess what it has to do? It has to level off.
Who's the weakest one?
Looks like Andrew's doing
It does, doesn't it? This is an exponential growth. This is a logistic curve. Now I'm going to put a star here for those who aren't listening.
Are they the democratic ones?
Okay, guys? The logistic curve is on the AP exam. It's a BC topic. It has been the free response. Actually, I kind of like it because it's so easy. I will give you extra practice problems on this. It's possible they will give us a logistic curve this year. Hasn't been for a while. Now it's getting to the point where it's just kind of like, what can I guess right on this one? Okay. Now, if we assume that this is the solution here, how would I know if that really is a solution there? Check. Because that's all you're going to do in the homework. You are not going to solve, you are going to check. So let's check that. It's dp dt. The left side is the derivative of that, and the right side is k times p. So we're going to go ahead and take the derivative of that exponential function. If I can make my page go bigger. Okay, so p is equal to p naught e to the kt. So what's dp dt? Remember, we can ignore the p naught and take the derivative of e to the kt, which is what? E to the kt times k. And this is kind of what the homework looks like. So we're going to put this in on the left side. So it's p naught. I'm going to put the k in the front, e to the kt. Is that equal to k times p? Well, p was right here. P naught e to the kt. Are those equal?
Yeah.
Yes. Now, this is also a multiple choice question on the exam. There are some that are repeated. This one is repeated. Now, I don't know if it'll be on the BC, but I know it's repeated on the AB. So when you get this differential equation, you need to know that the solution is going to be PERT. And there just is nothing else that works. By the way, if they gave you this differential equation and they gave you 5 choices for possible solutions, how could you do the problem? Do you have to solve it? Just take the derivative of each one and see if it'll work. Just like we're doing here. And that's what you're going to do in the homework. There's not that much homework. Okay. So this model only works when I have a small population. I've got a problem when things get bigger. And this is my little grid here. And this is the time axis. This is the population. This is called the carrying capacity, capital K, not the little k.
We learned about the file.
Yeah.
Good. Then this will be easy. Let's hope we get a logistic curve.
I've learned that right now, actually, in college.
So I don't want the population to be 0. There it is. That's a logistic curve. You will never have to solve the differential equation. Okay, listen to me carefully. You will never have to solve a logistic differential equation. So if they ask you to solve a differential equation, it's not logistic. Okay. Now, if the population is small, what's true about dp dt? It's just proportional to the population, right? But now, what happens if the population is bigger than the carrying capacity? Now, the carrying capacity is the max that your environment will sustain your population. So if it's up here, what's it going to do? It's going to decrease. So I need dp dt to be less than 0. And they're kind. They gave us a differential equation that might work for us. And there it is. And this you have to recognize. This is the last section of Chapter 7. So we hit on it now, and we hit on it again. This is a logistic differential equation. And it has to be in this form for you to find the carrying capacity. So if it's not in this form, you're going to have to do a little bit of algebra to figure it out. So it has to be Kp, and it's 1 minus P over K. That's the carrying capacity. Notice it's capitalized. Yes, we did this in free calc. Well, you didn't do a differential equation, but sure. So let's see if these two conditions that we have here work. Okay? Ready? You guys ready? No, you have to recognize it. Now, if this is a T here and a T there, that's a different matter. This is the population is proportional to the population and population. So, yeah, you could easily get it mixed up. I'll give you a problem that had them do that, and it was a free response question. So now, if P is small, what happens to this 1 minus P over K? If P is small, this is approximately equal to what? It's 1. So I do get dP dt is equal to K times P. I do get that, which was my first condition. What if P is bigger than K? Do I get a negative derivative? If P is bigger than K, then 1 minus P over K, is that positive or negative? It's negative. So dP dt, excuse me, would be negative. Looks like a good model. I'm not even going to tell you what the solution to that thing is.
I've already done it. I'm supposed to not do it.
The solution, you have to use partial fractions.
Yeah, I did partial fractions.
Uh-uh.
I said the K's are the same.
They're not the same, I wish.
Oh, that one.
Ah. Okay. Here's just a curve that we just drew. Now, if P is equal to 0, okay, you guys? If P equals 0, then what's dP dt? If P equals 0, dP dt is equal to 0. That's this. This is one of the equilibrium points. And this is connected to chaos theory, by the way. Logistic is heavily connected to chaos theory. What if P is equal to the carrying capacity? What's dP dt? If P is equal to capital K, if these are equal, then it's 0. This is the other equilibrium. Now, if you are doing chaos theory, this is called a repelling point, because everything here is getting pushed away from that equilibrium, but this one is being attracted to. So if you start with your population up here, it's going towards that one. So this is an attracting point. And that has to do with chaos theory. So if you want to study chaos theory, we could do some of that after break. But it would be up to you guys. Okay. Well, we really should do vectors, because you'll have to do vectors on your own in college.
What class?
The next level of calculus multivariable.
Not me. They don't offer it for accounting school. They don't offer
Okay.
it.
See, I already did this. dP dt is 0, and dP dt is 0. Okay, talk about equilibrium. It's the next page. And I talked about carrying capacity, and that's your model. That's it. Now, let me give you a little example. Let's do this. dP dt is equal to 0.02p, and it's 1 minus p over 400. What's the carrying capacity? Because that's what they're going to ask you. It's 400. Okay? That's it. It's very easy.
I can do that.
And, pardon? Little k is a constant. Now, here's the problem. They could give you something that looks... Oh, I know, but it's that easy. That's why I kind of hope for this. Well, but sometimes they're not like that. Like, let's look at this one. dP dt is equal to 0.02p, and it's 2 minus p over 400. It's not 400 now. Because remember, it has to be 1. So I'm going to pull out the 2, so it's 0.04p, and then it's 1 minus p over 800. That's correct. And they could do that too, and I've seen even trickier ones, and I'll give them to you. So carrying capacity is equal to 800. So that's kind of nice. Problem number 9 looks like this. On this part of it.
Yeah, we made it, right?
Pardon? Right, because solving that equation, I have to do partial fractions, but it gets kind of ugly. You could. Okay, so let's summarize the whole thing. That's what's on the next page. Where's the formula? It looks like there's something behind there. What does it look like? It looks like this. I don't know why they didn't use like a capital C. Yeah, I know. Okay, here's K. If P is between 0 and K, then my population is, my change in my population is positive, meaning that the population is what? Increasing. And if I start up here, bigger than K, my derivative will become negative, as we showed, meaning that the population is decreasing. What happens when you get really close to K? What's happening to PDT? It's growing slower, right? The growth is slowing down. Still growing. So this isn't a bad section. You can go ahead and read it. You're heading towards no population growth. And I kind of like the qualitative discussion here because it talks about the equilibriums. And it talks about the models. There are other models, but this one actually does things very well. It's quite sufficient for our needs, although it's not an easy differential equation to solve. Okay, what about a model for a spring? Now, remember, you guys have had physics?
Oh, I can do this.
Well, your force is equal to minus K, the spring constant, times how far away you move it. And force is mass times acceleration. So if I solve for acceleration, that's equal to, now acceleration is the second derivative, right?
Right.
And so it's going to equal minus K over M times X. Okay, so my second derivative is going to be some constant times X. The original force is some constant times X. What do you think might be a good function that would model a spring? No? Spring, it goes back and forth. Yeah, sine. Sine of t or cosine of t, that would be a good model. Because if you take the first derivative, you get to cosine. Take the second derivative, guess what? You're back to sine. Now, this is called, because it's a second degree, it's a second derivative, it's a second order differential equation. And unfortunately, the techniques we use for the regular differential equations, the first order ones, are not the same. Sometimes the things you do for first order ones work, but a lot of times they don't. That's what I wanted to say about the spring. But that's a nice little model, too. But actually, it turns out, you want to solve that? Okay. That's just a constant. So if I solved it, here's a solution that would work with the k's. Must be times t. And I should eventually get that to work. Oh no, it's what's in my notes. Okay. One last problem. Yay. And then what we're going to do is we will analyze, in this chapter, solutions to differential equations. Some can be done algebraically, some can't. We have a couple methods. We have slope fields. Remember slope fields? And then we have another method called Euler. And that's a BC topic. Okay. Solving a differential equation corresponds to measuring the state of a system at time t0 and using the solution of the initial value problem to predict future behavior of the system. This is the big idea. I want to predict future behavior of my system. And it's a system that changes in time. Okay, this isn't so bad, yours. Show that that's a solution. Actually, algebraically, it's not very nice, but we can do it. What do I have to do to show that this actually solves that? I'm not going to solve it. I'm not going to integrate. That's solving. Let's take the derivative and substitute in. So what is y prime equal to? Good review. Do you remember how to do this? Quotient rule is the denominator times the derivative of the numerator, which is c e to the t, minus the numerator, 1 plus c e to the t, times the derivative of the denominator, negative c e to the t, all divided by the denominator squared. Well, we're not going to square that. We'll just leave it. We can simplify the numerator. Okay, Matt? You want to come up and do this?
Yes, he does, Mr. G.
You guys don't like algebra. I love algebra. Okay, c e to the t, then it's minus c squared e to the t times e to the t, which is e to the what? 2t. Minus, oh, but this is going to become plus, right? c e to the t. And then a minus times a plus times a minus is also going to be plus c squared e to the 2t. Oh, it's not that bad, is it? All over 1 minus c e to the t squared. What's going to go here? Yep, that goes away. And so I'm going to get y prime is equal to 2c e to the t. That's not that bad. 1 minus c e to the t squared. That's the left-hand side. Now we have to do the right-hand side, which actually looks worse, because it was 1/2 y squared minus 1 all over 2. So this was 1/2 of y squared minus 1. And so y was equal to, I'm just going to write it so I can see it, 1 plus c e to the t over 1 minus c e to the t. Now, if you're going to become an engineer, you're going to be doing lots of algebra like this. Or you'll be using Mathematica or computer of some sort. So it's 1/2. Now I got to square this. This is the part I don't think I want to do. 1 plus c e to the t over 1 minus c e to the t squared minus 1. But it's really not that bad. Because you know what? The denominator is what I want. Don't I? That's what I want over there, so I want that. So it's 1/2, but let's go ahead and square out the numerator. So it's 1 plus 2c e to the t, right? Can I do that right, Sam? Oh, you're so trusting. C squared e to the 2t. Why is it minus? I'm squaring the numerator. I'm squaring the numerator. And I'm not going to square the denominator, at least not in the denominator. But now I have to subtract off the 1, which is the denominator squared, right? So I do have to square that one. Okay, so that's going to be minus 1 minus 2c e to the t plus c squared e to the 2t. Sorry, I ran out of room.
Is that minus?
Because it's minus 1. So I'm going to do 1 minus c e to the t squared. So I wrote that not right, but 1 minus c e to the t squared. Common denominators. And when I do that, I'm going to get some things to cancel out. What happens to the 1s? 1 and negative 1. What happens? Go. Okay, what else? I have a plus 2c e to the t, and this is also plus 2c e to the t. So I have 2 of those, which is good. And now what happens to the c squared? This is going to be minus here. Plus times a negative is minus, and that's a plus. So that's going to go, and I'm over 1 minus c e to the t squared. What happens to the 2's? That's the easy part. So it's 2c e to the t, 1 minus c e to the t squared. And is that equal? Yeah. And I did a lot of that in physics. Lots and lots of that kind of algebraic manipulation in physics. Being honest with you. But we didn't have computers back in my day and age. Not until I was a junior in college did we have a computer. And the computer was a mini computer, and it took up the whole wall. And we had paper tape that we'd feed into programming. Nothing like this.
Class do stuff like that, so they all do tests around the room.
I don't know.
They'll do like one problem, they'll do the whole one.
It can happen, and you'll run into that in math. You may only get one homework problem.
Did you multiply by?
I multiplied by this.
Yeah, is that the
The common denominator.
of-
It's just this denominator squared. So okay, I do this squared, get that out of there. So I squared this out, which gave me all, whoops, I didn't want to do that. Which gives me all of this, and then to get a common denominator, I have to have this 1 minus c e to the t quantity squared, so the numerator has to be 1 minus c e to the t quantity squared. And I just squared it out, and luckily, a lot of things went away. And guess what? There's more, but this is easy. Oh no, this is easy. Find the particular solution if you know it goes through to 0, 2. I'd rather call it 0, 2. Okay, so 2 equals, okay, we want to find c, you guys. So t is 0 plus 1 plus c e to the 0, which is not 0, 1 minus c e to the 0. This is easy compared to what we just did. Okay, so what have I got here? 2 equals 1 plus c over 1 minus c. How do I solve that equation? Cross multiply. Okay, Sam? So it's 2 minus 2c equals 1 plus c. If you solve that as quickly as I can, I don't know if you can. I'm going to add, I don't like to have negative numbers. So I'm going to add 2c to both sides. It fails because don't seem to care. 1 plus 3c, and now what are we going to do? Subtract 1.
1/3.
That's right. So c equals 1/3. That was the easy part. And the problems in the homework are not that bad for checking solutions, I don't believe.
And then when you write after you find c, you just.
So then I would substitute it back in here. So y equals 1 plus 1/3, because we don't care if we simplify, do we? 1 minus 1/3. My computer will still run with that solution written in that form. I would never change it to 0.3 because now my computer will not run correctly. I won't go the answer I did. So I thought I had one. Oh, should we do number 9 together? It's a homework problem. It is, but we can get number 9 done. Oh, wait till you see how easy it is. Because you know what? If we don't do it now, some of you will not do it at all.
Oh,
Oh no, I do. Yes, I am working on it. Now, the quiz for tomorrow is on the green packet, and you have to go into Skyward. You put it into Skyward. It's not great. It's corrected for you. It'll be a score, but it doesn't in the no count category. The quiz counts.
And what
Yeah, it tells you what the answers are.
What?
What?
Now let's.
We have a quiz tomorrow on the green packet.
Correct.
What's the green packet?
That was those AP multiple choice problems.
I don't think I have that.
There's another packet sitting over there.
Oh, got it. It's this one. This one, everybody.
Yeah. What's it on? When do we get it? No more than better.
Oh,
Oh, probably.
so easy. Now this is a type of problem they can ask you on the AP exam.
Did they ask us all of them the AP exam?
Oh yeah, because it'll be FRQs. Okay, what does it say? It says, for A, find the values of P where the population's increasing. Okay, Justin? If the population's increasing, what has to be true about dp dt? has to be greater than 0. Look at that equation. When is that going to be positive? P is less than 4,200. Can it be that easy on the exam? Yes, it can.
And I
Okay.
don't have that one.
Well, we can only hope. And then the next one is, when is the population decreasing? The population decreases when dPdt is what? Negative. What is that? Greater than. And the last, so this is what some of the homework problems are like. What are the, and you know, this is all the material for you, so you really need to do this. What are the equilibrium solutions? Not time to go. Okay, what are the equilibrium positions?
4,500.
No.
200. Zero.
What's the carrying capacity?
4,200.
When do you think this is, the population's changing at its fastest rate?
Middle, right.
Exactly where?
Derivative.
This is 4,200, this is 0. It would be at the inflection point, which happens to be exactly halfway. It's 2,100.
Yes. All right, let's test on this
Wait,
right
so
now.
what problems do you want us to do that?
It's whatever's in the assignment sheet.
Did we get that today?
Yes? That was the other one?
Oh, it looks.
And then you can go back and you'll find logistic problems.
Equation instead of the other one.
Pardon?
Why do we use this equation instead of the other one? The AP one.
Because that was what was given.
Oh, it's it. Oh, let's do this one.
They told you to use this. Population's modeled by that. But yeah, you only have about 10 minutes where you could be working on something. So have a seat, because it's not time to go. You know that clock is not working. Oh,